All right.
Tara was a buddy of my buddy and so on. And at the time it came up in the late 60s, early 70s maybe, we decided we were going to do the same thing, try to do the same thing. We figured he did it because he had access to computers at Los Alamos that most people didn't have access to. So at the time. So what we surmised was that what he did was work backwards. He started with the film and he says, well, each point on the film is an eye, so to speak. And then he would project the light cone back and see where it intersected the world lines of the sphere. And then say that, well, that's what the signal is going to be here. And so on. And he did that at all these different places, huh? Or a sample of them. And then on the basis of that, he concluded that what happened when the sphere would rotate. We figured also he didn't do a sphere. He did a ring. But he could just kind of scale the thing. And we were going to try it again, but other things intervened. So that's what happened there. But I'm pretty sure that would be the way to settle the issue, right? Calculate where the light cones intersect the world lines of the sphere. And you're not doing part of the story that our friends here gave this morning. We're talking about projections from down here to up there. The photons are going from here to down there and drawing, but the photons don't go instantaneously, which is the point I made here. They take time. So when the sphere is over the camera, directly above the camera, you don't see it. You see the camera. You see the signal coming from a previous location. And the second thing is, it's not a stream of photons, it's a spherical wave from each point. And you add up all the spherical waves from all the points on the sphere and so on, and that will be the signal that you, and so on. And it's very complicated, very tedious. You can't do it on paper at all. Not unless you, somebody better than I am.
Next story out, now they will begin.
Oh, okay.
Time dilation.
Time dilation, yeah, it's not just a spooky or mysterious effect. It's not interesting to me because it's just a mysterious effect. It's actually a very profound problem because if it's true that there's time dilation and the twins are not the same age when they get back, then there's a number of things that follow from that aren't so cool anymore. And of course, the main issue historically has been was brought up first by our friend Herbert Dinkel, huh? And the expression on his face, I think, tells the story. Herbert's point was that there's a lack of symmetry here, so you can draw any conclusion you want that they don't match up. You can go further than that. You can say, well, actually, every charge, every electron, every charge was a traveler who started at the Big Bang. And every other charge can consider himself as a stay-at-home twin. And then apply the principle. If there is such an effect, then every charge in the universe has a different age. Not only that, but you can turn it around and say, well, every charge in the universe is actually a stay-at-home, and all the other charges are travelers. So then, he has a different age. In fact, you have a different age with respect to every other charge. So every charge has, what is it? Eddington, I guessed at the number of charges in the universe. The number of charges, in the universe is something like 10 to the 80th or something like that. That was his number. Probably bigger than that. At any rate, that means every individual and every electron has 10 to the 80th different ages because they're all and so on. It's absurd. That isn't a proof of anything, but it's a symptom of error, I maintain. And not just
at least a symptom of confusion.
Yeah. It's not, when I say I don't want to be too egocentric here. There's a lot of people who hold the view, and I'm just one of the proponents. Yeah, here I just make the point again on this thing. And then now the next point I'm trying to make here, this is sort of foxy against blank things, is that if it's true that each particle has its own separate, different proper time, then it becomes impossible to write an equation derived from either Hamilton mechanics or Lagrangian mechanics that fits the general patterns of Lagrangian mechanics. Now, the overall meta principle of these mechanics principles that they're derived from is basically that energy is conserved or something like that. And what that means is that there's everything that happens in the world being considered in that mechanical system is caused by something in the world. There's no exterior inputs or outputs. If you can't do, because for whatever structural reason, that there's because of this Einstein thing, I don't know if it's Einstein or whoever, but because of the twin effect, if you can't do it, that would mean the universe is really unstable, or the mechanics is wrong, or something is wrong. So I think the fact that we would like to have an equation like this is a relativistic equation, a wave equation, for all the particles in the universe coupled together. So this is a multi-particle system. Nobody else writes this equation that I know of.
So psi here is a universal wave function.
Sorry? Pardon?
Psi here is the universal, the equation of the
Yeah, right. Psi would then be the wave function for the universe.
Yeah.
Yes. And nobody writes that equation. What do they write? Well, they write an equation for one particle bathed in an exterior field, and the further assumption is that that particle does not talk back to the source of the external field, which is a very restricted approximation for such an equation. If the equation like this were to exist, then each particle would interact with all the other particles in some way or another. Now, there's another story to tell in this whole thing, and that is how do you get an interaction story? How do you get an interaction term that is itself soluble? The classical meaning just that they were done earlier, stories there is sort of the Wheeler-Feynman one, where they talk about the interaction with every particle is the sum of an advanced and retarded interaction. Now the problem with that is that if you believe this, then you get a set of equations for which you can't find the solution without knowing the solution. Again, proves nothing, but it's certainly a symptom of a big problem. If, on the other hand, you can come up with a kind of interaction that eliminates the forward part and just accommodates the backward part, then you have a system of equations and a story to tell that is consistent with what we kind of think about the universe anyway. We believe that the past has influenced the present, but not the future doesn't come back on us. So by cutting off the Wheeler-Feynman type integral at tau, which is that tau, and you can write this. This makes sense only if there's one of these. If there's one for each particle, n of them, then lost in the woods again. So the equation itself, just in my mind, is sort of a minimum set of requirements in order to have a logical, reasonable sort of kind of relativistic physics. This is special relativistic physics for the universe. And since the principles behind the derivation of these theories are all kind of things we don't want to live without, namely conservation of energy, coherent, integrable equations, equations for which you don't need to know the solution or to find the solution and so on, then this is the problem. So, that's what bothered me a long time, and I came up with this story. Now, this is a Minkowski chart. In fact, it's several on top of each other. And every single thing depicted here can be found in a textbook, but not on the same chart like I wrote it here. The only thing on this chart that is different is the final conclusion. But every step along the way is a step that you will find in all the textbooks. There's two charts here that should be obvious. Huh? The black lines are the coordinates for the stay-at-home. The blue lines here are the coordinates for the traveler, as they would appear if you write them on a black line chart. There's nothing mysterious about that, really. Then here is what we're talking about now is the trip that the traveling twin makes. What he does is he goes out from somewhere to a star or something and turns around. That star is, I call it the pylon, which is the, makes allusion to old-time airplane races, right? Airplanes would go out to some turn around the pylon. If it were a sailboat, you would call it the buoy, and I don't know what you call it otherwise. But at any rate, the word pylon is short, it's on charts. So the pylon for the traveling twin is located at some star, and it has a world line. And it's a black world line. It's out here at distance d from where the stay-at-home is staying at home. That's distance d. Now, the next thing is to look on there is the green lines. The green lines are the isobars. And the green lines tell you where a given point on the black chart winds up when you take the same value and put it on the traveler's chart. So the question is, where is the pylon on the traveler's chart? Because the traveler is going to meet the pylon. So where does he meet the pylon on this chart? Well, in fact, this point D here slides up the isocline to this point. And therefore, for the traveler, the world line of the pylon is this here blue line. Now, then the pylon's world line is, of course, his time axis. So where does he meet the pylon? When does he get there? Well, you go out here and that's the point where he meets it. The turn event for the traveler in his frame. And so what time is that? Well, what time is that? It's that time there on the T minus, but if you take that down the isocline and go back here, you see it's there. And that point is exactly the same point as this one. And what that means is that even though it looks like there's some time dilation for the traveler, there really isn't any time dilation. In other words, this is only half the trip, of course, but the other half would be a flip-flop of these lines. There's no actual contraction. What people appear to be doing, it's never discussed in textbooks on relativity, is they appear to be forgetting about this transformation in one way or another, or not taking it into account just right. Something along those lines. Getting a little vague about it all. But when you take it into account this way, you can't miss it. The other thing that people do, of course, almost everybody, including myself a lot, is talk about transmissions of photons or signals or whatever without explicitly and carefully delineating the difference between the point of origin, the time of origin, and the time of reception. They start sticking T's into formulas, into Lorentz transformations, and they put the wrong T's in there. They put the transmission time in there, and then start trying to conclude things about the reception. You have to keep in your head very clearly exactly what time you're talking about when you're talking about transmission. We saw that this morning here. The time here and there is delayed offset by the transmission time, and you got to be very careful what you're doing down here to make sure that your transmission, the formulas have the right time. And that's, of course, that mistake is made by mistaking this point for that point, and so on and so forth. So that's the guts of my story, really. If you eliminate those errors, then you conclude, well, there's really only one proper time for the universe, and you can write the equation I showed before. But there's a number of other kind of ancillary type things. One of them is, what about the evidence, experiments? Our friend, do experiment, right? One of the customary experiments for testing time dilation, of course, is this muon story. What they do is they go up on a mountaintop and arrange to have a block of scintillator up there, and they count flashes in the center of the scintillator. Then they take the whole kit and caboodle down lower and add some more material above it to compensate for the slowdown that occurs to charges traversing the atmosphere, and again, count flashes. Then start analyzing it by saying, well, all the muons were created at 15 kilometers in the sky. All the muons were created at 15. Really? This is a curve that shows the intensity of flashes in the atmosphere at different heights. The interesting thing about it is that that height of 15 kilometers, of course, up here, but actually further out, there's even less flashes. Which shouldn't be the case if all of them were happening out here, say. So what this says is that as you go down in the atmosphere, the number of flashes you're going to see is higher, and then it'll tail off. And that, of course, reflects the fact that there's such a thing as secondaries, tertiaries, and whatnot. That is, the various cosmic rays, and who knows what they all are, precipitate a shower of stuff, and they keep precipitating that shower. And the shower itself multiplies a little bit. So that you can't talk about analyzing a stream of muons, in my view, without taking into account the fact that more muons are being generated as the shower proceeds. Secondly, the cross-section of muon generation, I think, has to be, I've not seen this in the literature, and I'm not an expert on nuclear chemistry, so I'm not exactly sure here, but it seems to me you have to assume that the cross-section for muon production, actually it's pion production from the charges, they say, and then the pion decays right away to a muon and so on, but those cross-sections have to be velocity dependent. All other electromagnetic cross-sections are velocity independent. Therefore, you can't just say that all of them were, all of the muons were generated at 15, and we counted them, and then we went lower, and there were too many. Well, maybe there are too many because you started here and you wound up there. In fact, the classical experiment, the one that's for which there's a little pedagogical film produced at the time in the 50s. Huh? Yeah, it's right. It's a muon experiment done in Mount Washington. Fritsch and Smith. Yeah, and Smith. They compared. What they really compared, of course, was again flashes seen in their scintillator at Mount Washington, which is about I think it's about 4 kilometers. Maybe not even that much. No. Was Mount Washington about 5,000 feet?
6,000 if it's the one.
6,000 feet?
Yeah, I've been up it many times.
Yeah. So 6 kilometers. So they compared the number of flashes there with the bottom of Mount Washington, was also 1,000 feet, I think. And so they were somewhere down in here. And so the decrease in the amount of, you would see just from this curve, is not as dramatic as they, not anywhere as dramatic as they think it is. The other experiment I know about a little bit is one done by people in Colorado, where they did it, I think, at Leadville and at Boulder. Leadville is 10,000 feet, 11,000 feet, something like that. Boulder is 5,000 feet. So they're somewhere up in here, and I don't know what their actual numbers were. I didn't ever find that, but they claimed again, once again, that saw more muons. I'm not qualified to throw rocks at there, because I just don't know the chemistry that well. But I think I see enough here to justify suspicion and to ask for really careful analysis of those experiments and whether or not they're showing anything.
How about if you want beam insert?
Pardon me?
A muon beam insert, maybe?
This isn't the clean way to do it. The clean way is just to look at the particles at a certain. The clean way to look at muon decay is just look at the muons, generate them, and look at them.
Yeah, how do you know what you have before you've measured it? I mean, how do you know you're looking at muons? Maybe you're looking at some original charged particle. Because all you're counting is flashes.
No, what happens?
And they identify them by coincidence.
We could discuss it, but the profile for a muon or a pion is very different going through.
Yeah. And
they don't just go through, if you've got a 200 jet muon, which was the muon beam insert, it doesn't just go through one detector. It goes through a beam detector, you see it coming, it then goes into a set of calculators, and muon has a profile.
I know. I took off one time and I was going to go start analyzing that, and I didn't get very far. Maybe I should. I have intentions of doing it, but at any rate.
Can I produce a comment?
Yeah.
On a much smaller scale, the same question comes up about dealing with many co-moving electrons.
Yeah.
When you're dealing with a multi-electron atom. Now, I have a friend at the National Chemical Laboratory who regularly calculates the wave functions for 16 electron atoms or a bit larger, and gets very accurate numbers out of her very heavy data crunching computer program. So she's proving that the multiple electron wave functions, albeit only 16 instead of 10 to the 16 or 10 to the 60, all right, can be handled, but she doesn't deal with them, as you suggest, in the co-moving frames of each electron. You are dealing with them in the co-moving frames. But when you deal with atoms, you just write down the Slater determinant. Okay?
Sounds familiar. Yeah.
Right? So I ask you, why does her system work? It's not using your prescription.
Well, my prescription, I hope, is aimed at determining whether or not the muons are actually living longer. I'm not much interested
Are you familiar with the big number of experiments on K mesons?
Not in detail, but I know all of them. Yeah.
There's the kind of K which decays into 2 pi's, and the kind of K which decays into 2 pi's. And they've done hugely detailed back in the 1970s, 60s and 70s, on the behavior of these mesons. And that was what led eventually to the discovery of charge conjugate, wasn't it? Charge? Time reversal. TP violation. Yeah, TP violation, which is the same as C violation. I mean, people have thought about co-moving frames like this for individual particles in quite a lot of detail.
Yeah, I don't know exactly how to interpret what you're saying in terms of proving that there's...
Alan, in simple terms, if you take something at low energy, it doesn't go as far as if it's at high energy, but it's the same particle. And that correction is just relativistic.
I know that. I know I'm swimming upstream here.
Yeah.
I know I'm swimming upstream. But if I go with their story...
Yeah. My story.
Your story. If I go with the story, whosever it is, that there is concrete ontological time dilation, then I arrive at horrendous, ridiculous contradictions. Like every particle in the universe has a different time, and Hamiltonian mechanics doesn't work, and we can't write down wave equations that make sense.
But you're carrying, I seem to think that you're carrying the classical picture of tracking each particle into quantum theory. But in quantum theory, you don't do that. You write down a universal wave function.
We're talking about relativity, not quantum theory. It doesn't really matter. There's nothing essentially quantum.
Interesting story.
Whatever it is. The story is interesting, so please go ahead.
Yeah.
Yeah. Well, basically, this is where I am. I mean, this is a work in progress because I've still got to deal with the various arguments that they've observed time dilation. I'm trying to find reasons. I'm trying to unravel that story and see what they really observed. I know all their in these muon experiments, what they're counting is flashes, and they identify the character of the flashes by coincidences. And they have different, the scintillator has 3 different layers of scintillation on it, blah, blah, blah. And if the 2 flashes occur in such a way, then it had to have been a pi, blah, 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 blah.
If you give me
Not
your
very
email
convincing.
address,
Huh?
if you give me your email address,
Yeah.
I will get the answer that is considered reasonable by the man at the National Institute of Advanced Study.
I know, I'm swimming upstream. I know these guys got credentials where I have open air. I know that.
Who's worked on the muon experiments with cloud chambers.
I know.
Are you,
I think he's a real neutronic.
do you know about the muons?
Yeah, in
of
CERN, yes.
And they have storage.
I know. I've looked at it some.
Yeah, and I think that is a very precise measurement, and there's nothing which disturbs the path of the muons.
Okay, I agree. It's very precise. But I know in muons you've got you're measuring scintillations, and there's a track between where the particles are generated and where they see the scintillation, and they assume they know where they're coming from. And my preliminary thinking is that there's one can get charges from decays in the muon track from any point on the rim.
No, I don't think the case will leave the storage.
I don't know. Huh?
Because there's a condition for that mass in the storage room. And just measuring what goes in and what comes out, how many go in and how many do you lose?
Yeah.
That gives you a number, and it's vastly larger than the state than 10 to the minus 6 seconds.
You know, but there's very, very little in physics that we observe directly.
Yeah, but this is...
And there's physics is built, the observations are, there's a whole series of inferences, and deductions, and consequences, and so on. And anything in that chain.
But you talk about learning 1,000 times longer.
Ah!
I mean, that's
How many people, take the world of religion. How many people believe this, believe that? If you're going to argue that because a lot of people believe it, then you believe in some, I mean...
This is just a measurement.
The human being is capable of believing anything he wants to.
True.
And it could be that some...
I'm not convinced with that.
Is this the end of your talk? Because I would like
This
to
is the end.
okay, fine. Then I would like to add a comment.
Yeah.
You know, I also did a lot of thinking about this muon decay. They basically, it all falls back to these 2 axioms of special relativity. You know, that the speed of light and the physics is always the same. Now, I've gone away from that, and I can...
What's you saying?
The physics is always the same.
Yeah.
The chemical reactions, or whatever you want to call it,
Yeah.
the interactions are always the same. Now, I've gone away from that and have and allow let C vary, and also allow you know, and question the physics. You know, if we take just the light emission of an atom, we say when it moves there's the red shift. You know, or in a gravitational well there's a gravity dilation or blue shift that we observe. But I can also show that with my physics that I can get exactly the same time dilation and the gravity shift through the Bohr model, you know, without going into special relativity. Now, with that in mind, and going to this, what Al is saying, the question to ask if this delay of the lifetime of the muon is because it just has more energy because of the kinetic energy. It is not the same particle as a stationary particle, you know, because it's different, you know. So, you know, although these experiments are there, we interpret them into special relativity. And, you know, we should also consider interpretations that might not be special relativity.
That's a possibility. but it does follow exactly the special relativity thing, which would be a...
Yeah, no, it's...
Or somebody's tailoring things. Huh?
No, it's not...
It wouldn't be the first thing. No, they don't do it deliberately, but they know if they get the wrong answer, they're not going to get funded.
No, look...
So they got a problem. And the solution is pretty easy.
With the work that I've done, I've come to the conclusion Einstein is right for the wrong reasons.
Yeah.
You know, which is, you know, E equals mc squared. I fully agree.
Yeah.
You know, E equals root mc squared again squared pc squared, you know, all squared. I fully agree with. You know, it all comes out. It's a geometric interpretation. And it's not particular. It might not be special relativity.
Yeah, I'm more or less at the end of my rope, my leash. I don't have enough expertise in nuclear chemistry to really criticize those experiments, but just from general principles of how science is done in those areas where I know where I'm on better footing, I don't have any trouble suspecting that there's a fly in the ointment.
I would not say there's. I think we have to value the experimentalists to be honest people, and that the results that they show us that those are the same results that I would see. You know, I always say I see the experiments through somebody else's eyes. You know, that I think, you know, without that, maybe I'm a sucker for
trust no one.
Trust, you know. So I think, you know, I'm always going to look at the latest results, but I also see if one can interpret them in another way.
No, I trust no one. As far as I can say, what I complain about is bad wording. You got something that's usually said light speed is constant, and that's just bad wording. And so you sort of consider something like a thought experiment, two people measuring vertical speed. I'm not going to tell you whether they're moving or not with respect to each other. So just consider that. Given one, light speed is constant, and two.
You're taking quotes out of my translation.
Is this what I'm sorry, if it's probably.
Is that right?
Maybe. I've read bits of your thing. So
did you read, what's the original German and compare it with that?
I don't know. I don't know.
That's the issue. That's the issue with the translation. Those are things Einstein said.
Okay, no. Consider like one, light speed is constant.
Yeah.
Two, person one measures vertical speed as c. What does person two measure? Treating that as logic, 1, 2, consequence 3. Person 2 measures light speed as c.
Look,
and so it's just the bad wording.
Yeah, I don't know that it's. I want to agree with that.
Yeah.
I'm not one of the people that considers Einstein a saint.
Yeah.
I think he was a very competent physicist, as physicists go, and human beings go. And he was very productive. He wrote a lot of papers on a lot of different things, and he got a lot of things right.
Yeah.
Now, I've done a little bit of papers on a little bit of things, and I've gotten some things wrong too.
Yeah.
And that's just, you know, we're all humans, and that's the problem. Einstein deserves respect. He was one of the top dogs of his day, but he made mistakes. Of course he did. And he was in that context at that time.
Yeah.
He was working with what he had at that time. And he did a lot with it.
Yeah.
And a lot of people now throwing rocks at him they're making their own mistakes.
No. I mean, considering that.
I happen to hold him in very high regard.
Yeah.
Because he's one of the few people who, in the face of actual insults, persisted in maintaining that quantum mechanics is an incomplete theory.
And he was right.
And he was right about that. That's one place he stuck. He took his position. He made his arguments. And he said, people consider me a nut. Well, the German equivalent at the time, it was a little bit more elegant than my phrasing here. But he said, this is how I see it. And he wrote one of those papers 2 weeks before, or he published it 2 weeks before he died. So obviously he didn't change his mind about that issue.
He said one of the last things he sort of said was something like, building castles in the air.
I don't remember that. There was a
quote though. He sounded like everything he did was wrong.
If then everything I do is wrong. Yeah. But that had to do with the photon, not with
Are you going to get on to talking about what the problems are, or?
For what? No, I'm basically through. I thought it would precipitate a good discussion, and let's have it.
Good.
So I'm confused about you, because I have tremendous respect for you in the first place, let me say that.
Yeah.
You are
now it's gone.
a brilliant physicist, and I really weigh everything you say very well and seriously. So the way you started out the talk, I thought, yeah, maybe there is a problem there. So this is at least interesting. Your Minkowski diagram, I have to study and see if I make the same mistake or not, and whether or not this is right, and why it might be right or wrong or whatever. So this is my homework that I have to do, because I have to really understand that. Right or wrong, I have to understand it. It's going to teach me something. So that is going to, this is something you've already given me. But now about these new ones, I know this has been with you for a long time. I'm completely confused, because there are actually many experiments that show that there is something like time dilatation, and it's also gravitational planes that fly with atomic clocks around the world or whatever. Yeah, there's the satellites.
That one is easy to discuss.
Yeah, okay.
That one's easy to discuss.
But there's satellites.
Kelly, you know Kelly, the story Kelly pointed out, it's this guy Kelly, he's an Irish physicist. He happened to be something of a pro on atomic clocks. And he happened to have pointed out that at the time that around the world, what's the name? The two guys who did that. Yeah, Halfway and Keating, right. Halfway and Keating, right. At the time they did it, the atomic clocks, the variation in the atomic clocks was 4 or 5 times bigger than the effect they saw.
Okay.
And they cherry picked. They had 10 atomic clocks to begin with, and they used them all in the experiment, and then they threw out the data from a couple because it didn't fit.
Okay, then you just go to the satellites that are going flying at the moment for your GPS and everything.
Yes, okay, GPS I can answer. GPS is not a relativistic system. It's an Earth-centered system.
Forget about it. Forget about it. I mean from Philips. In Philips we have developed the basic electronics for these things, and relativity comes into the equation. So
relativity, I can
to make them accurate, it just comes in. If you don't do it, you only get it to 30 minutes.
There is a time delay in the perception of the signal.
Also that. Also that.
Can I just answer this?
Yeah.
GPS design principle. In the satellite, you have to make the clock.
My opinion is the following.
Now, I'm stationary in the satellite, so the Earth clock's going to move slower, or why? You know, the satellite clock is I can't remember, slightly less than the Earth clock, you know, so that they match up again.
You know, you can tell me anything you like. I have seen people doing relativity to get it right. And then I get systems and they work. And you know, they can only be right because they've done it right.
The formulas are correct, but I can do that. I can exactly the same.
Right, it can be right because you get the same transformations for doing it in a different way. If you start thinking about frame dragging, for example, is that what you're talking about?
No, I'm not frame dragging at all. I'm using a completely inner Cartesian coordinate system. In the same time, I get exactly the same result to do exactly the same 14 digits that these clocks are tuned to.
Well, I'd like to see that.
Yeah.
What the analysis is behind it.
So that's the thing you say. The other thing is a system that works. And that system that works is more believable to me than just a word, although I like you tremendously, you know that. So, but this is the, I'm purely
Once upon a time, not long, not so terribly long ago, but a while back, I looked into GPS satellites, right? So I read about it and I discovered that there's an agency in Switzerland that sort of manages the calculations done for GPS satellite. And supposedly they had an openly available paper or something on the corrections. So I started plowing around to see if I can get a copy, and sure enough, you can get a copy. And when I got a copy, I got a stack of papers that thick. Obscure, you know, it was like the calculations you do for all the pipes in a chemical factory or something. And at the end of the day, I concluded I wasn't going to sort that out.
That's not the way you can get through. No.
I know they have a story. I know they have a story. I have a story.
You have a story.
They have a story. So
I know you have a story,
and if the twins don't come back equal, I think the story is easy to understand in terms of the perceived, and that I believe. When I look at a tree in the distance, it's bigger than it's smaller than my thumb. That's I believe that, but that's just geometric, right? But in space-time, and you're right. There's a space-time perspective thing in there, and I think that's the effect that one way or another they're actually measuring. But there's no ontological time dilation. There may be all kinds of reasons why it goes slower, from general relativity, from this and that and the other thing.
I know you can be easily fooled in relativity because I mean I'm using it myself, and you can sometimes you can
I
fool
will send you
yourself.
some programs and you send me that.
Yeah. On the other hand, I am not in any way obliged to do somebody else's work, right?
Anyway.
So I have to understand my stuff, and I try to understand your stuff, and so I'm responsible.
Let's get some time here, Chris.
Well, I think if I were you, I will start from the relativistic wave equation, which is the Brown's proposal. So your analysis here, I mean, I would not throw away Einstein. I agree with the ontological part. I completely agree with the ontological part. But I will not start from the Schrödinger equation as you did.
No, I didn't start there. That was a separate argument.
But you wrote that equation.
I wrote, yeah.
Okay. The point is that if you start with analysis with the relativistic wave equation.
No, actually my analysis had nothing to do with that equation, except to make a backhanded argument.
That's the completeness of the...
I make a backhanded argument. I say that equation, as it's written, satisfies the meta requirements for a self-consistent. And if you don't want to write that equation, then you wind up throwing out meta conditions like conservation of energy or something like this.
Okay, but that's part of your analysis, because you said that that something will be understood. Could not be understood if you have the tau there that has not.
Right.
Okay, so perhaps you do the other way around. You go start with the complete, the Broglie equation, the relativistic one, that is part of the issue of the completeness, and then go carry out the analysis. But the thing is, the question is that the solutions to those equations, to the general equation, are harmonic solutions. I may repeat again that there are new solutions to a wave equation, and those solutions have a very interesting property. Those solutions have the property that they are isomorph both to any other transformation, so both to the Fogel transformation and the Galilean transformation, which are classical, they are Doppler transformation, and are the same exactly solutions for the Einstein transformation or Lorentz transformation. So all the parts that they mentioned correctly about the time dilation of the muon in the lab, which is correct. I agree with you. Those experiments are cannot be believed. I mean, I just wrote them, and after the second page, I say they are wrong. But the other experiments in the lab, at the accelerators, they seem to be right. So, but what happens then? That if you interpret those in the terms of the new solutions, there is no problem, because they are consistent both with your classical way of seeing things and my classical way of seeing things, and with the relativistic way, be it Poincaré, Einstein, or whomever.
Did you have something to say, Albert? You were making noises before. Do you want to chirp up here somehow?
No, I don't understand what you mean.
Did you want to say something?
No, I've said about this, that was enough. I think dilation is clear if this is still the topic. And, I have no problems with it. And I think there are enough proofs. We have worked on the data in Hamburg and we have this problem all the time, and it was calculated and all calculations did work. So why have doubts that this is correct? Yeah, that's what I think. Perhaps I have the occasion to say a little bit more that it supposes that has to be assumed that there is a time gap left for me tomorrow.
There's too much going on here. We'll talk later.
If you want to ask a question about
GPS satellites have to be constantly updated because of continental drift.
Every 3 seconds.
Yeah, every 3 seconds. All right.
What does that mean?
Well, everybody was worried about the.
Yeah, I know. But that's what I found in this stack of papers.
Well, okay. Thank you, Albert. That was very interesting. We finally had a discussion.